Recording in progress.
Okay, let's go ahead and start. So thanks for coming. This is a joint CS Applied Math colloquy, maybe the first ever, I don't know. So we're very happy to have Tammy Kolda here speaking. I've wanted her to speak here for a long time, and she's finally here, so we're very happy. So normally I write down like a little post-it note of like awards for the speaker, and that's a mistake with Tammy because a post-it note is too small for all her awards and things like that. So she's very well known. So she's, well, where to start? So she's a fellow of SIAM, ACM. She's on the National Academy of Engineering. She has the Presidential Early Career Award. She has many Best Paper Awards. I know her 2009 review paper on Tensors is extremely well cited. A lot of us know that paper. She has 25,000 citations overall. Works a lot, very famous for tensors, but also just in general, scientific computing, data science. For data science, she started the SIAM journal Data Science that started just a few years ago. She's the founding editor-in-chief. Her PhD is from Maryland, right? Baltimore County. Yes. Okay, College Park. And she's been at Sandia for about 20 years until last year. Now she's consulting and traveling, and so she's here. So without further ado, let's give her a warm welcome and thank her for being here.
Thanks, Stephen, and also to Jed, who I think is like online somewhere. Thanks for hosting me today. Yeah, so thank you. That was like embarrassing, but I'm going to talk to you today about something exciting tensor moments of Gaussian mixture models. If you know any of those words you're ahead, don't worry, I'm going to explain all those words as we go through the talk. First, I want to acknowledge my co-authors. Joe Cleo is an assistant professor in math department. So we met and I gave a talk, and he came up and asked me questions afterwards. So I love questions afterwards. So keep in touch. And then Joe was also, they work together at Princeton, and Joe is now a postdoc at Texas, and he's going off to Brazil next year to be a math professor. All right, so I should say, you know, people ask, we had this career session earlier over lunch, what do you like best about the field? And I like collaborating. So getting to collaborate with these guys has been a big bonus. All right, so where are we starting? Why are we going to even talk about moments and tensors and all this stuff? So basically making sense of data. So, you know, a lot of times in my life as a data scientist, I'm in my data science house, what I get is a pile of data and help me make sense of that data. So here's an example where someone just, you know, pile of points in 2D and just happen to be 1,000 points. So what can we make any sense of what we see here? Are there any patterns? And so one thing you can do is try to create a probability distribution from your data. So try to understand the density of the data in this 2D plane. And so you can think of, you know, here, the 2D plane is sort of shown here, and then the probability is the z-axis in this 3D model. I could create something like that. So just to give you sort of 2D level curves, if I look at that from the top down and draw the level curves, the yellowest is the highest. And then I can sort of, I think, yeah, put that on top of the data. And so this is just sort of an arbitrary probability distribution where the highest points are sort of the highest concentration. The highest levels in yellows are the highest concentration of points. So a lot of times they're interested in discovering models that describe our data. And so that's kind of the focus of this. So one very standard model is a Gaussian distribution. So, you know, it's bell curve in 1D. So it's also known as a normal distribution. And so I'll symbolize that with an N for normal distribution. And so here we have some random variable X, which is an n-dimensional random variable. So the example I just showed you that n is 2, so 2D variables. And then it's defined according to a mean and a covariance matrix. So how do you use those? You have this probability just density function that you can write in terms of mu and sigma. That's never going to come up again. You don't really have to worry about that function. I just show a picture. So here's a picture of what it looks like for the 2D example. And so the mean tells you where the highest point is, the center of this bell, and the sigma tells you the shape of the bell curve. So this is a simple one. It's just concentric circles centered around the mean. And it has nice properties, this Gaussian distribution. It's the limiting distribution of the sum of random variables. It's symmetric around the mean mu. And the marginals, if you just look at it like a 1D slice, and it's also normal. So there's a lot of tricks around that. And so then you just remember as a bell curve because it kind of, whoops, it kind of looks like a bell. All right, so, and you can choose different covariances, but you don't choose them, but they might, different covariances might exist. The one I just showed you is the spherical covariance. So often this covariance matrix just might be the identity or some multiple of the identity. It just gives you circles. You can have weirder ones. You can have what they call diagonal or axis aligned. So maybe one axis is skinny and one is longer. So that's sort of a simplifying assumption. And then you can have the most general assumption is just a general covariance matrix, and then you have a sort of a tilted circle, and it can be ellipsoidal. So those are different choices, and then they sort of go up in difficulty as you make more and more general. All right, so we have a mean and a covariance that define a Gaussian. So we could try to fit a Gaussian to this data. So we get something like what we show here, and if I show the level curves, you might say, like, that's okay. Like, I sort of know where the data is. If I look at the whole of the 2D plane, at least I know where it is. It's not really capturing the data. The highest point is most yellow. It's actually kind of a blank spot here, and there's really nothing here. It says there should be. So then you can go, okay, let's get a little more complicated. You can do a mixture of Gaussians. And so this just means I'm going to say how many Gaussians, like user-defined parameters. So in this case, it will be M. And then lambda j will be the probability that I'm in the jth Gaussian. So that's the M is the number of components. You can think of lambda j as the proportion or the probability of picking the jth component. And then you have a bunch of these normal distributions. And so the picture here is you have several bumps, and each of those is a Gaussian. And then they can have different shapes of the covariance matrix can be different shapes. A tilted one, a circular one, the axis aligned one, and you can have any of those in one. And this is a powerful model because you can actually, if you use enough of these Gaussians, you can just describe basically any distribution. All right, so now, if I was to say, here's this data, I want to run a Gaussian model of that, to first pick the number of components, so I'll say 3. And then for each of those components, I can run the parameters lambda, which is sort of proportion, mu, which is the center, and sigma, which describes the state of the circle. So if I do that for this one, I get this here, which looks really good. And that's because I generated the data from this guy. Is perfect. All right, so that's a Gaussian mixture model. And so it has lots of applications. So one is density estimation. You've just got some points, you just want to understand what's the distribution. And so you try to infer a Gaussian mixture model to know that. It's used a lot in practice, like for clustering of data. So sort of standard applications, market segmentation. So people who own cats and like sci-fi, who knows how people segment markets, but there's a lot of directed advertising and a lot of money in that. And then things like anomaly detection. So I kind of Googled on anomaly detection, everything's like fraud in financial, fraud in medical, fraud. There are other places for anomaly detection as well, but this is one of the big sort of application areas. And those are just some examples of where you use Gaussian mixtures that you turn up in a lot of places. And so, the example I showed you was 1,000 2D data points. Real world scenarios, I'll say very conservatively 10,000 data points, and then maybe like 500 dimensional data. We want to deal with much, much bigger data sets. And in practice, if you go to industry or even some of the examples that we work in science, this can be even higher than that, but just to give you a sense. We've been picturing things in 500D is hard, and working with tens of thousands of data points, or millions or billions can be much harder. Okay, so that's Gaussian mixture model. Any questions about that? All right, so we're going to be trying to learn those, but before we go to that, go through various tensor things. So tensors and symmetric tensors, we'll talk about next. So a tensor is just a multidimensional array. So a vector is a tensor of order 1. A matrix is a tensor of order 2. Here I'm showing a tensor of order 3. And so we usually call D is the order of the tensor. So there are various ways to picture fourth order tensors, and I'm going to use that to your creativity. The best I can do right now is 3D tensor in the picture. I'm going to also assume that all the dimensions are the same n by n by n. So it could be n by n by p, generally speaking. And then a D-way tensor where each dimension has size n, has n to the d entries. We call it the cursive dimensionality. It's very big. And so that makes it sort of interesting to work with these. Aijk is just the ijk entry of the tensor. So just like a matrix is Aij, or a vector is Ai. And then we can say a three-way tensor is symmetric if any permutation of that ijk, if you look that up, you get the same number. So there's 6 different permutations you get here. And so all those should be equal, then we say the tensor is symmetric. Just like with a matrix, it's Aij with Aji. This is all those different permutations. If you do four-way tensor, you get 24 permutations. It goes on and on. And symmetric tensors arise in a lot of places, including higher order derivatives, right? So Bobby Schnell worked on eons ago. And so they're very important in a lot of areas. There's also a cursive notation. You have D indices. I'm not going to do that to you. We'll mostly do just IJK. A few times we even need to index. All right, so then just do a few operations with these things. So if I have 2 tensors, I can think of inner product of those. And I just match the indices. So I take Aij times Bijk, and then sum those all up. So it's kind of a normal inner product. And the norm, just the inner product of A with itself is the norm squared. And then you can do this trick where if you take the difference in norm of 2 tensors and you square it, you can do this kind of standard trick that you could do with vectors or anything, which is the norm of A squared plus the norm of B squared minus 2 times the inner product of A and B. So we're going to actually use that a lot. All right, so now let's talk about symmetric outer products. So suppose I have some n-dimensional vector B in Rn. So I can take the outer product of B with itself, which if you were writing it in matrix notation, it'd be B times B transpose. But we use this funky notation where it's B cross with a circle B, and that's an n by n matrix. We also sometimes use this shorthand B with a little cross circle 2, so that's what we're doing twice. And that gives us a matrix so that the ij entry of the matrix is Bi times Bj. So just take the ij entries of B. You can do a 3-way version of that. And so I'll take B with itself, outer product itself 3 times. So B circle 3, and that just means the ijk entry of this n by n tensor that I get out is the I times the j times the k entry of B multiplied together. And so sort of a picture of that is shown over to the right. So we get B, 3 vectors B, and we get this n cubed output. And you can go further. You can go 4th order one. So if you're starting to get the pattern, and you can go all the way up to order D. You can take D-way outer product. So that's the symmetric outer product of a vector with itself. All right, so why am I telling you about this? So we're going to connect to something called statistical moments, and I'm going to connect those back to Gaussian mixture models. So let's say we go back to this random variable stuff. So let's say we have an n-dimensional random variable. So we can ask about its moments. So the first moment is the expectation of this n-dimensional random variable x. So this is just me. You know this one. We're in safe territory. And the ith entry of that is just the expected value of the ith random variable. So it'll give you a vector in Rn, and it's just a normal mean vector. And we can do the second moment. So that's a matrix, and the ij entry of that matrix is the expectation of xi times xj. So if you centered your data first, so you subtracted off the mean, this is the covariance matrix. You do the third moment. So this is just the ijk entry is the expectation of xi times xj times xk. And you can keep going on from there. So you can do up to the dth order moment, and then you get sort of what is the expected value of the products. And just like, it's not obvious, this is not obvious to me, like the expected value of x times y is not equal to the expectation of x times the expectation of y. Random variables are funny. And so these are all potentially different things, and that's why they become interesting. And so these are always symmetric tensors. So this is why we're talking about symmetric tensors. And so the method of moments, what it does is it looks at a model, and then it looks at data and computes the moments of each, and then tries to match them and use them to that idea to find the parameters of the model. So I have some general idea, and can I write these moments in terms of the parameters of the model, and I can calculate them from my data, and then can I match them? So that's the basic idea, and it goes back really far, for like 1800s. And then, yeah, so we're going to focus just like on matching the dth moment, or just say the third order moment. Really, you want to match all of them. At the very end, I come back and tell you how we match all of them by matching one of them. All right, so a bit more about tensor products. So if we take our third order, we can do a third order tensor outer product of a vector with itself. We saw that. What if I do something weird, like take a vector times an outer product with a matrix? So it's kind of the same rules. I'll take the ith entry of this times the jk entry of C. And it's not symmetric, so that gets a little bit weird. But you can do this. And you could take B times C, and then it'd be Bi times Bj times CKL. So I'm just taking the ith piece, the j piece, the KL piece. I can do C cross C. And I'll take the Ij of C times the KL of C. So any questions about that? And then I'm an artist. This is my vector outer product with the matrix. It still gives you a 3D object. All right. Now here's where it starts to get kind of fun. You can take a non-symmetric tensor and you can symmetrize it. So if you did it with a matrix, you just take like 1/2 A plus A transpose. With a tensor, if it's a three-way tensor, there's 6 different versions you have to add up and just take their average. So we call that the symmetrization operator. And so sometimes you have to do that. We're going to do that here. So just taking all the different possibilities and averaging them. And if it was already symmetric, this operation would have no effect. You get back the original tensor. So one of the interesting things is if you have a symmetrized tensor, you take its outer product with something else, you can actually throw away that symmetry operator, which is very expensive. Like we actually calculate these things. You could like take your tensor 6 ways and then add it up. You don't want to do that. It takes a lot of space and memory. So it turns out if you're just using it inside the outer product, just throw away the symmetrization, which is kind of a big like fancy math step. So that's kind of a neat result. All right, so now we'll get back all the way back to Gaussian mixture models and their moments. So yeah, so this is our big funky theorem. So we have, just for a regular Gaussian, not even a mixture, I have a random variable x that is normal distributed with mean mu and covariance given by sigma. And I want to calculate its dth moment, which is the expectation of all these different xi, xj, up to d different ones. I have this formula here to tell me exactly how to do it, which is in terms of the mu and the sigma. So this looks really ugly, so don't look at that. Let's just look at some examples. So the first order moment is mu, we already knew that. The second order moment, so if I've not centered the data, so mu is not 0, it's the outer product of mu with itself plus the covariance. So if mu was 0, that would go away, and it's kind of what you expect. The third order moment is mu, the outer product of itself 3 times, plus 3 times the symmetrization of mu outer product with sigma. And you can keep going. So here's sort of my artist rendering of that. So it's the outer product of mu plus 3 times the symmetrization. And you can actually find papers that really write this out. Like if you can imagine what all the entries of this look like, ui, sigma, jk, like they actually write it all out. So it gets very complicated. I think this is easier. We even have 4, and you can keep going all day, all night. So now I have this general formula for the deeper moment in terms of mu and sigma, which is ultimately what we're going to be trying to find. All right, so this is going to make things simpler to work with. And now just hint, we have any like algebraic geometry people here? Okay, 1, all right. Oh, another half, okay. So the cool thing is that you kind of get this by a 1-to-1 correspondence of these symmetric tensors and homogeneous polynomials. So yeah, So if I can write a function that comes from A in terms, I can write it as a multivariate function in I should say n variables for an n by n tensor that is just aijk times zi times zj times zk. So I can sort of go back and forth between tensors and polynomials. And so one interesting thing is that the two polynomials are equal for two different tensors, then their symmetrizations are equal. If A was just a one-dimensional tensor, then its action as this polynomial is just this inner product of A with the input Z. If it's a two-dimensional tensor, it's just Z transpose AZ. That's what that function turns out to be. And then a really interesting thing is that normally when you switch the order of these two things, you don't get the same tensor. But in the homogeneous polynomial world, it's just the product of those two homogeneous polynomials. You can swap those, that's fine. And so it kind of gives you this ability to commute your entries. It's kind of a very powerful result. And so, did I hear a question? Yes. Yeah, exactly. Yeah. So presume that the question was, can we think of it as a characteristic polynomial of the tensor? Yep. And so the main takeaway is you can completely characterize a tensor in terms of just its inner products with an outer product of these z, with this z vector. So this idea of working with the tensor through inner products turns out to be really useful. Let's see, what we're going to say here. Oh, okay. So it's just going to kind of give you an outline. So the idea of the proof, and like, I don't expect you to really, I'm just going to give you like little nuggets. You should read the paper. Is that we want to sort of figure out this moment, that's this expectation of this x to the power d. So we're going to think of this in terms of a univariate Gaussian that's based on the dth order moments. When we make it in terms of z, everything reduces to inner products with z, so products with z. And now we have a univariate Gaussian, and then we can, once you have a univariate Gaussian, you can just pull that stuff out of basic textbooks. Getting down to this is sort of tricky, and making it into polynomials is just sort of helpful. There's maybe other ways you could do it. And then we end up using things about marginals, multivariate Gaussians. There's a lot of stuff here. You don't really have to know all that, but if you think that's fun, then you could go look at the paper. If you don't, skip that part. Isolated proofs. And so there's like something here for everybody. If you want the proofs, they're there. If you want more numerics, it's there. If you want more statistics, it's there. This result, now if we know how to do a single Gaussian, thank goodness, the mixture is really just the mixture of what we had. So we can just sum up all the ones for the individual Gaussians and weight them by lambda, which is missing from here, but there's a weight of lambda in there. And oh, so each of these pieces is exactly for one Gaussian, and then we just weight them by the same weights of the mixture model. So now I can, if you were to tell me the mu and sigma, I can just tell you what the moments are. So this will turn out to be how we can use to find the mu and sigma if we didn't already know them. All right, so now let me kind of bring into focus. So we have a model, we know the mu and sigma. I now know how to compute the moment, the dth order moment for that thing. So for the third order, it's this. And then the parameters I want to find are the lambda, the mu, and the sigmas for all of the components. And we're saying that you already know the number of components, like in this case, 3 components. And then I have a bunch of data. I haven't talked much about this, but I want to compute the empirical moment. So for every dot here, I compute the outer product of itself 3 times, with d times for general d way. I just take their average. You don't actually want to do that, by the way. That takes a lot of time. And a lot of people actually do it, but I'm going to tell you, you don't actually want to do it. It takes a lot of time and storage. That's the average of all these outer products. And so then I want to match those. So I want to choose these parameters so that it matches what I see empirically. So that's the big problem I want to solve. I want to minimize the distance between the empirical moment on the left and the theoretical moment of the model on the right. And so and you're like, well, did we get the right formula? Like we just came up with this formula. So we did check on like several examples. And if we look at the number of examples, the number of dots As you increase those, you expect that the difference between the model and the sample moment to go to 0, and it looks like it does. So one wrong minus sign, that's all off. All right, so that's what we're going to do. And the idea is then we know this should go to 0 as we get more and more samples. So we can use that to actually learn the parameters. So there's the number of parameters is m times 1 plus n squared. So this is the covariance matrices. If these are diagonal, this just goes back to n. So why should we make something n cubed to find only like n squared parameters? Seems like overkill. So maybe we won't ever actually make this n cubed thing. That's kind of what we want to avoid. If you do 4th order, you're doing something n to the 4th. You definitely don't want to do that. All right, and then in the input data, the number of data points you have is p of them, and they're each length n. So we want to learn these parameters from p times n data. All right, so now we'll come back to this idea of how can we do this method of moments in the case of a Gaussian mixture model. All right, so here's our Gaussian mixture model. We have our empirical moment that we calculate from the data. We have our model moment that is based on our parameters, and we want to minimize this difference between the empirical moment and the model moment. We can cast that as an optimization problem. So we just have to be able to calculate this difference and then also compute its gradients. So I'll remind you about this inner product of 2 tensors. We've talked about that before. You can also do an inner product of outer products. So if I were to take the inner product of tensors created from that, when I break it down, this A outer product 3 times B outer product 3 is just outer product of A and B, like I'm saying outer inner product of A and B cubed. So that's kind of fancy. And you can just actually generalize this for the D way. And you can do other weird things like outer product of A times the outer product of B and C. And you get something similar where it's A transpose B. So you take the inner product of A and B and then A transpose CA. So all kinds of fun formulas you can come up with, and there's sort of a general form of that. This is kind of what you saw in that crazy formula earlier. And so now I want to do this as an optimization problem. And I know this in terms of the model parameters, which are mu, sigma, and lambda. That's optimization. All right, so now we're going to think about how to rewrite this optimization function. So this is a squared, norm of a squared plus norm of b squared minus 2 times the inner product of a and b. So that's the first thing we did. Now, this is just a constant. So it doesn't really affect the optimization. So I don't actually have to calculate that unless I just want to highlight a feel good that that's going to 0. A lot of times I do want to have that feel good, but you don't have to calculate it. Then I have, so this is a constant, and then this I can rewrite as outer product of all the different pairs of outer products, as I'm doing the sum, so all the different pairs there. And then this is the outer products of all the pieces here. So I move the sum outside. So this is the outer dot product of 2 moment tensors, or the inner product of 2 moment tensors. And this is the inner product of a moment tensor and the sample moment tensor. The model moment tensor and the sample moment tensor. So I'm going to do how to do the second one first. So just for the 3rd order case, focus on this guy. So in the 3rd order case, the 3rd order moment is this formula here. And I want to calculate this inner product. So I'll just kind of plug this in and just split it into 2 terms. So I get what's here. All right, so we already know how to do this one. We can basically pull the 3 to the outside, and the symmetry we can drop because it's inside an inner product. So we get this next line here. That's already simpler, but this is still a little complicated. But remember, we kind of already saw how to do that. And so this is just taking the inner product of this with mu, and then this times the matrix back times the vector. So now we can calculate that. So that's that second term. I just told you the 3rd order, but we have general functions for the dth order. It actually gets kind of complicated. We're using these things called Bell polynomials. We're not going to go there in this talk because I like you guys. This one is even worse. So I'm not going to say too much except for to say this also is a lot of bell polynomials, and we end up kind of using the idea that we end up thinking of this as a single random variable, and the dth moment of that. Anyways, don't worry about all the details there. I probably should have taken this one out, but I'll say see the archive paper for details. But we can do it efficiently. This is sort of the main thing. We can do both of those terms very efficiently, and in particular, we never ever form the moments themselves. All right, so we cast it as an optimization problem in terms of lambda, mu, and sigma. And so we never ever need to actually make these cubes of data. Those are just things that exist mathematically. And so we're overcoming this curse of dimensionality. So we never need to create n cubed objects for the d equals 3 or n to the 4th objects for d equals 4. The function can be calculated efficiently. We just showed you sort of the secrets, but it never uses more than m times n squared storage, which is basically for all the covariance matrices. If they were diagonal, that squared goes away. And then the total work is never more than m squared n cubed. And this n cubed is we have to multiply the covariance matrices together. I didn't tell you where, but we got to do that. If they were diagonal, again, all the n cubed stuff goes away. And so this is actually the same amount of work as the other popular method for fitting these into expectation maximization. So this is the same work for sort of function evaluation. I haven't told you how, but we can do all the gradients too. I just sort of go like, no problem. It took months and months, years, I don't know. It took a while, but we can do that as well. And it's kind of the same basic ideas, just stretched a little further. We can also do fun things like if we have a lot of these, like p is 1,000,000, I don't want to do this for 1,000,000. I could take random samples and do sort of stochastic gradients. It actually works really well in practice. In fact, I published an earlier paper and I said, you can do this, and the referees didn't believe me. So I was like, great, now I'm going to put it in, because it's actually very simple. It's a common technique that people use, but it actually just worked great and it's good to show it. There is something that's a problem, which is an inherent scaling problem. So I'm going to spend the last few minutes before I get to numerical results talking about that. So if I have these two Gaussian mixtures, so the top one is just half of mu1 sigma 1, and then the other half goes to mu2 sigma 2. And then I have another random variable that's a little bit different. It's a quarter for this normal distribution, and I've just kind of scaled mu and sigma. And then I changed this. This is now 3/4 of the second one, and I've scaled mu2 and sigma 2. These actually have the same third order moments. So if all you have is a third order moment, you can't tell the difference between those two. So what do? So the general idea is I can put in an arbitrary gamma sub j to sort of weight things and get the same dth order moment. But it does depend on d. So one way I could fix that is just look at other moments. And that's kind of what we do. So the problem is the moments of order d are the same, but one thing you do is you've got a bunch of random observations, these n-dimensional vectors. You just can append a constant c to the end of every vector. And then this is kind of a standard trick. Then when you're going back to try to recover things, you know that's supposed to be c. And so then you can use that to recover things. And in fact, what it turns out, I have this here, yeah. By adding that c, I actually magically get all moments when I do the dth moment. This term ends up picking up the d minus first and d minus second moment because it interacts with that c in weird ways. I don't want to go into it too much here. I probably drew up a picture for that someday, but you implicitly get a weighted combination of all the moments up to order d. And so just sort of magically drops out. So it's kind of fun. And we don't know how to choose that constant. That's actually kind of an open question. It does affect how much weight each of the other moments has. And there are potentially other things we could do that sort of forces a weight on all the other moments. We could do other things as well. All right, I'm going to pause here before I go to numerical results and see what questions you have. Go ahead.
Okay. Yeah. So can you center the data, or is it not, because it's a mixture, you can't center it, so you have to assume this mu is non-zero.
The mu j's are non-zero. You can center the data, and actually, I don't know, a big question, a big pragmatic question is, How should you pre-process data? You know, the moments get very big, very fast. So, you know, what's the best way to do this in practice? But even if you center the overall data, the mu j's won't be 0. Yep.
For the C, you get depending on what you arbitrarily choose C to be, you'll get a unique mixture, but there's nothing that says what those different mixtures have. Like, there's no way to specify particular qualities with that. Is that correct? You want to choose a C.
Right. So you think of it as we are the kind of mixture here is different mixtures. That you get like a weight for the first moment minus the empirical first moment minus the model first moment squared, plus another weight that depends on C, the second order moments, the difference between those, and then another weight for the third order moments, and so on. And so it kind of, and that C, those weights for each of the, how important they are to the objective is determined as a function of C. But I thought I should put that down. It's a good question.
So kind of as a follow-up, right? I imagine that choosing M is kind of a model selection question.
Oh, yeah.
So, I mean, if you have kind of a method to choose M, couldn't we use kind of a similar idea to also say, how do I choose C so that objective?
Yeah, I think so. Yeah, we haven't even investigated, but that would, I think, definitely be a real investigation. Absolutely. Yeah, and choosing M is, you know, it's a big problem in these mixture models just in general. There's a lot of
basic
proposals to do it. Yeah, Bayesian is one, yeah, certainly one very popularly. Another question?
Is there a comment for the these moments for how frequently this nothing show up?
Yeah, so the question is there a combinatorial, just sort of, say it again, let me check it right, there's combinatorial.
Combinatorial interpretation for nothing show up with the term person element.
Yeah.
And could that be used to help inform how it thinks?
Yeah, all right, yeah, so there's a, yeah. I can know what you're saying without being able to do the combinatorial, so that this polynomial that you get that's connected to these tensors, how much each thing is weighted, each of these unique entries is, yeah, it's a numerative comment, but you can figure out combinatorial function. And then, so some of them actually in some ways get counted more than once, these differences. I have like a whole other paper on that, but it doesn't seem, I haven't figured out if that helps or not, but. And then, yeah, we haven't done it with the C, but that definitely affects it. Yeah, I think it's pretty wide open. I think this is like people are interested in this, and it's a hot area for follow-on questions.
I wonder if there is a connection here with special hypergraph theory.
Oh, special hypergraph, very interesting. I don't know. Yeah, maybe you know that. That's kind of cool. Other questions? Great, thank you for those questions so far. All right, so let me just show you some numerical results, and then we'll kind of wrap up. So, so the state of the art for fitting these Gaussian mixture models in every like software package ever for doing anything in data science is expectation maximization for these. And so the basic idea is you make some initial guess for your parameters. These things are really sensitive to that initial guess. It's also like 1,000 people know how to do it, and most of the software has something decent implemented, but that does matter. And then you're trying to maximize the likelihood of the observed data given the parameters. So then you take the log of the likelihood. The likelihoods themselves are actually very tiny quantities. So you take the log and it becomes some big negative numbers. As you're trying to okay. You maximize the log likelihood. Because I'm an optimizer by training, I always want everything to be minimization problem, so I negative effect, but for statistics, you think of maximizing the log. And so the way that you do it is you sort of compute how much each data point is a member of each of the proposed clusters, and then you update and then you kind of just look at the members of that each Gaussian and update its parameters. So sort of fractional memberships, a little complicated, but and then you kind of go back and forth. You don't try to solve the entire problem at once. So that's EM. It's very efficient and very speedy. And if you have enough data, you can always find the parameters using this method. So it's inexpensive. It's relatively easy to implement. There's some gotchas that you got to be careful about, but otherwise it's easy to implement. It is optimizing a different cost function than what we optimize. We are optimizing this moment matching. and they're optimizing log likelihood. These are different cost functions, which is maybe good, maybe they have different pros and cons to them. It's sensitive to initialization, which I already noted, and then it's pretty sensitive to overlapping clusters. So if you think of those bumps, as the bumps move closer and closer together, it's harder to tell that those are two distinct bumps. And so, and that seems to be where it gets caught at. And so method of moments has a lot of theoretical advantages. I think I told the lunch group, I don't know if it's lunch group or some other group, but I started working on this thinking that these method of moments things were used in practice. I read too many theory papers. I thought it was real. And so I like tried to improve on that, thinking it was real. And so when we went to try to compare to these other implementations, like, oh, they don't exist. But they are studying these in theory because they can say a lot more definitively how many samples you need to determine the parameters, and in some ways nicer theoretically than expectation maximization and log likelihood. So I offer this not as a superior method, but as an alternative method. And you never know, like different scenarios, different methods are useful. And I think it's never really been examined for multidimensional, multivariate random variables because it's really hard to compute these moments. And I actually got interested because some of my colleagues were like computing these high order moments. And I was just thinking, why are you taking p times n datum and making them p times n cubed? Like, why are you doing that? It feels wrong. But maybe you can do it implicitly. That's kind of the genesis of a lot of this. So go ahead.
So EM is, iterative, but this mom is exact, assuming you do that trick with the C's.
So
To get rid of the non-uniqueness.
yes, so mom, we will approach it iteratively. There is for the third order moments, and I'm trying to think if they need any assumptions on the covariance. I don't think so. The third order moments, if it's noise, like in theory, you can solve it deterministically.
Once we get quantum computers.
I don't know that you need quantum computers. I think it's noise gets you on before quantum, like before the need. It's not that.
But I mean, the argument to use this instead of EM is that you have a nice formulation that's not just approximate.
I would say that it's now because we have a nice formulation, you can now think about using it. and then I'll show you a couple examples. We do have examples where it can outperform EM, but I'm not saying like drop EM and use this. It's more like if this is something that you can explore, there might be certain advantages to it. We're still like getting there. We just made it now possible. Do that, yeah, the way I think it'll be great. So I'll give you two examples. So we knew it's with overlapping Gaussians, it's going to have the best performance. If it's separated Gaussians, EM, almost any net, so very easy. So we have overlapping Gaussians and diagonal covariances, just to keep it a little easier. Because we actually literally have to write a whole other paper on how to do the full covariance matrices. We have all the math, but just getting it all written down is a little bit tricky. We'll do 100-dimensional, we'll do 20 Gaussians, so the mixture of these 20 bumps, and 8,000 observations. It's actually a little bit of a low end. We think there's sort of a sweet spot where we can do a little better than EM. So EM, if we have like 100,000 observations, EM would probably be fine. And so there's two different we're going to compare two methods, just EM, and then the method of moments for the third order, and then the fourth order. And then we'll do 10 runs of each, and each of these dots right here is the result of one run. And we have EM in red, the method moments 3 in blue, and the method moments 4 in green. And so the first sort of picture here, is the EM objective function. So it's trying to maximize the log likelihood. Weirdly, the method of moments did it like a little bit better. That's a surprise. And then if you look at the third order objective function and the method moments for the fourth order, it's like seems to be less sort of variance in the points they get. They're kind of always going to their minimizer. Part of it just might be the sensitivity when you're taking the log of these very small values. You see that they do split for the EM, but we have questions about the landscape. Is the landscape more attractive for these method of moments? That's sort of the open question. And then in terms of runtime, we're a little bit slower than EM for this example, but like by a factor of 2. It's not a big deal, and it might literally come down to implementation. We didn't make it that optimal. And so those are just things you can measure if you only have the data. and you don't know the underlying model. And the bottom line is I know the underlying model because we created this data. So how well did it find the different pieces? So if it's better on all these. If we look at the lambda, so the weights, and we look at the one norm error, so it's 20 components minus another 20 component vector. Smaller is better, so the two method moments do better. If we look at the error in the means, we just look at the two norm error, it does better. If we look at the covariance, I don't think we have enough observations to get that super accurate, but maybe better, but at least as good as EM. And then this is an interesting one. This is something we often do in tensors. We don't necessarily look at the exact vector, but is it vector pointing in the right direction? And so if we look at the cosine between the true vectors and the ones that we found, and these methods find it sort of perfectly. So the cosine is 1, it's a perfect match. But I only go down to 0.85 here. So it's not that the other is so terrible. So that's one example on just the same setup as before, but we made the entries in the covariances a little bigger, so higher noise. And then what do we see here? So EM actually optimizes its own objective function best. So that's a good sign. And then these other methods do the best in the third and the fourth. And you can see the method moments 4 does do a little better in optimizing its objective function. Now these method moments are a little bit faster. This is a harder problem, so EM struggles a bit more. And then still, so we got faster runtime. So I would say that these runtimes are comparable. They're optimizing different objective functions, but the same cost per iteration. And so that's in like order of magnitude, same cost per iteration. And then we see that it's still doing well on all these different metrics, except maybe the covariance. It didn't capture as well, but these are high noise problems, so we probably need more data to capture well. But we're seeing that these have, in a constructed example that we knew was hard for EM. I can't stress that enough. I'm not saying like EM is done. That we knew was hard for EM. We can see that there's some advantages to this method. Any questions on that? Yeah.
So when you have non-fake data, you don't know the true M, that's a hyperparameter to both. But mom additionally has D as a hyperparameter.
Yeah. Yeah, and one thing is you could even solve with EM. Sometimes you like solve with EM, but you don't know if you trust your solution. So you could even just calculate these objectives for the different order moments as sort of a validation for EM. So you look at how well do the moments match. And so that's, maybe it's just even, you don't necessarily use it to fit, but use it as like a secondary test for the quality of your solution from EM. Or you could even imagine mixing these two objectives. There's a lot you could potentially do. All right, so I kind of made allusions to related works. There's been a lot of work in the theory regime, which I've found pretty interesting. Stu and Kakati have been involved with several of these. This 2015 paper with Guy, Wang, Kakati, they were kind of inching towards what we were doing, but they didn't know the symmetrization operators. It's just kind of a gnarly paper to even work through. And then more recently, kind of from a community that is also kind of in this algebraic geometry, they're also kind of sniffing at the same idea and kind of focusing more of could you, can you find these parameters, and how many samples you need to find that. There's been computational approaches in machine learning. There's a lot of excitement about these 2014 papers on orthogonal symmetric tensor decomposition, which I've actually weirdly never liked those papers. So that's been an offline discussion. And yet, I think they're really important. And so they kind of are in the same theme of work. And then a couple years ago, my sort of very tippy toe step into this was on very simple problems. It was very simple version of this with sort of diagonal covariances and a lot of assumptions that were completely unrealistic, but you got to start somewhere. And so that sort of was a stepping stone to this. And the big thing we did there that was different was implicit computation. So how can you avoid ever forming these big moments? So I feel like that made these problems tractable that people didn't think were tractable. And then weirdly, we found one of our formulas up to third order and a thing about comparing kernels. And so, these ideas are kind of out there in a way. So what's different for us is, we had this way of writing it down in terms of tensors. that I think reveal structure of the problem, like you can get rid of the symmetry operator, that is useful and makes things much more tractable. And a lot of these earlier papers had various constraints on the covariance matrices, which people often impose in practice, to be fair, but that they're spherical diagonals, we don't assume that. And then another big thing is it's all very computationally efficient. So this paper is a beast, let me tell you. So yeah, I don't envy the referees. So the takeaways here, so our focus is on this method of moments, particularly for the Gaussian mixture model. Another question is, what about other models? Yes, good one. I'd be happy to talk about that offline. So we were able to formulate this model for the Gaussian mixture, formulate the moments of a Gaussian mixture model in terms of its parameters using the quantity tensor language. I'm going to explicitly write this down. We avoid in the computation and the storage ever having to form these n cubed or n to the fourth objects. And this is a big practical thing. I wonder if people are like, why would anyone ever have done that? But they're doing it. So we're trying to get them to stop. And then we have this way of doing scaling ambiguity, which is novel in the sense that it turns out to like reveal things about the moment. But this adding of an appendix is kind of standard. And then it's amenable to being stochastic. And there's some stuff we didn't even really talk too much about. There's a way to take any data and sort of scrape off Gaussian noise using some of these same ideas. And there's lots of future works. It's implementation details. So in fact, some people even already have like tried to implement this as we posted on Gaussian and showed us some bugs in our pseudocode. We're going to also, that was just diagonal Gaussian. So the full Gaussian is just going to be hard to write it all down. But I think we have code for it. Analysis of the optimization landscape, especially compared to the maximizing the log likelihood. This is a very exciting field of machine learning, is looking at these different landscapes and maybe choosing certain neural nets have better optimization landscapes than others. It seems to make a difference. So we're curious if there's anything here. We were inspired by all these theory papers that tell you how many samples you need, but we haven't analyzed that for this, and I'm not really sure we know how. And then application study. So thank you for your attention, and everything's in this archive paper if you want to know more, or email me. Thanks.
So we have time for one or two quick questions, and then we can stay offline and ask more questions later.
Yeah, thank you all for coming. And thanks to the online friends. I don't know how many are there, but thank you for coming.
In your, it seemed in the numerical results, the only place where this method of moments was sort of like losing to EM was in the like first runtime result, but even there it seems like you have the same theoretical like asymptotic ones.
Yeah.
So I guess my question is like, why? Like it seems like this is just better, but are there any like distinct drawbacks compared to EM?
Well, thank you for saying that. I think it's just like mathematically kind of ugly and complicated. Probably the main drawback, honestly. Yeah, I think there's quite a new one. They have the same cost per iteration, but since it's different objective functions and we're doing it iteratively, we actually don't know how many iterations it will take. And that's where maybe one or the other might have a better landscape, and that's kind of an open question.
Does this have more, like, are the storage requirements for this?
They are exactly the same.
They're the same.
Yeah. Yeah, the storage is the same and the cost per iteration and the optimization is the same. So yeah, thanks. I think I saw. I thought I saw you reading. No, we're gonna do okay. No. Fair enough.
Are there any Zoom chat questions?
Nothing so far. Oh, one just came into the chat. So
That's a long one. You want to ask them to unmute?
yeah, Nathan, do you want to unmute?
Oh, yeah, sure. Yeah, sure.
Hey,
This might be a little weird because I can hear myself. The coefficient expression for the deep order matching moment. So those coefficients have a combinatorial meaning, and they come up as coefficients of these Hermite polynomials, which also have connections to Gaussians. So I was wondering if Hermite polynomials played a role in your proof.
That's a great question. Hermite polynomials, I do not believe played a role. But we use these things called Bell polynomials, and I would not be surprised if they are related.
Yeah, the Bell polynomials are kind of a heavy hammer. So maybe there's a way to do it with just Hermite polynomials. I don't know. I'd have to read the paper.
All right, yeah, if you could, I'm writing this down, just send me an email, or at least I know who to give credit to.
Yeah, in particular, that coefficient is the number of K matchings of KD, I guess that would be. Where KD is the complete graph on D vertices.
Yeah, great, excellent. Yeah, I've learned a lot about numerative combinatorics. I didn't even know that was a topic before this project. Now I have a book on it on the shelf, so. Great, thank you for that pointer.
Great.
Yeah, no problem. Yeah, no problem.
Go, and then if you want to stay around, maybe you can answer some questions.
Absolutely.
So let's thank Tammy again.